Hi, Ketzbook here, and today we're going to be looking at nuclear fission and nuclear fusion, and we're going to also try to learn the basics of how nuclear weapons work. So let's get into it. All right. Now, initially, scientists that were looking at this stuff weren't actually trying to find a way to do nuclear fission. All right. They were originally back about 100 years or so ago looking at elements like uranium and seeing what happened when they exposed them to neutrons. And they found that they were able to actually make new elements. All right. And this is known as artificial nuclear transmutation. So, uranium 238. So, uranium, the most common form of uranium is uranium 238. When it's bombarded or given neutrons, it will absorb the neutrons and then turn into things like neptunium. And neptunium was a completely new element to scientists at the time. And they can make a whole bunch of other elements this way too. And so scientists kept on trying other different elements and different isotopes of uranium with neutrons. And for example, they also tried uranium 235, which is less common. But when they tried uranium 235, something totally different happened. So uranium 235, when it absorbed a neutron, rather than turning into a different element, it actually turned into and split into two lighter elements. And at the same time, a very large amount of energy was released. And they right away recognized that this is something profoundly important because it gave off a lot of energy. In addition to the energy in the two lighter elements, it also gave off two new neutrons, or sometimes three new neutrons. Now, that is also very, very important. All right. So notice that the reaction takes in one neutron but gives off two neutrons. This is fundamentally different than any kind of nuclear decay. Remember, nuclear decay does not have anything else over here. Nuclear decay typically just has some unstable nucleus on the left and nothing else. So nothing initiates nuclear decay. This is different. Now we actually have some kind of nucleus and something else. Okay. And so this is a reaction that you can actually control the speed of. You can actually control what happens because you have two different things here. It's not first order decay like ordinary nuclear decay. Now, what happens is because we have two neutrons that come out, or sometimes three neutrons that come out of this nuclear fission process, and a new one neutron is absorbed in the process, that this is going to be a self-accelerating type of reaction. So the more that it happens, the more neutrons you have to initiate new nuclear fission, and the process can continue again and again and again. And we can look at it this way in kind of a more pictorial way. So in this process, here we have uranium 235. It absorbs a neutron. It makes the unstable uranium 236, which doesn't last for even a fraction of a second. That instantaneously splits up into two new lighter elements. And the two elements that it splits into are not always the same. So in the previous case, we saw it's making tellurium and zirconium. In this case, it's making krypton and barium. You have more than one possibility, but it's going to make two new, more stable, lighter elements. And it's going to give off sometimes two, sometimes three neutrons. And those neutrons can each go on to hit a new uranium and initiate the process once again. That is known as a chain reaction. Okay. So if you start off with just one neutron, you're going to make two or three new neutrons, which can bump into more uranium atoms, which can make now, let's say, up to nine new neutrons, which can hit nine uranium atoms, et cetera, et cetera. So if you have all of these neutrons being absorbed, this is going to be a self-sustaining chain reaction, which means it's going to, once it starts, it's going to continue and go through the entire material, and it could end up in a nuclear explosion because it happens so, so quickly. And in that process, a whole lot of energy is going to be released. In order for you to get a self-sustaining chain reaction, you need something known as critical mass. Now, the critical mass basically is the minimum amount of fissionable material needed for a self-sustaining chain reaction, right? If you have less than the critical mass, so your mass of your fissionable material, such as uranium 235, if that's less than the critical mass, then you're not going to get a self-sustaining chain reaction. Why? Because too many neutrons will escape and they're not going to be able to cause more fission reactions. So what you can really look at is these two diagrams, this one on the top and the one in the middle, really kind of show what's going on. So a neutron is not going to be sucked in like some sort of tractor beam kind of thing. It's not going to be sucked in by uranium 235. It might bump into a uranium 235 or it might not. And the longer space or the longer time it has, the more likely it will bump into a uranium 235. So if you have it in a fairly small sample here, you're going to have a fairly large surface area and fairly small mass, and that those neutrons are going to likely leave the material before they bump into another uranium 235. Okay. If, however, you increase the mass, you're now going to decrease that surface area to mass ratio, or surface area to volume ratio. And those neutrons need to go through a much larger space before they leave the material. And so they're going to be much more likely to bump into a uranium 235 atom and split it. So, the critical mass is essentially just that minimum amount of material needed for that self-sustaining chain reaction. Okay. Now, another way you can achieve the critical mass, and there's multiple ways you can achieve the critical mass, is what if you have some kind of material that's able to reflect neutrons or bounce the neutrons back into the material? In that case, you can actually have a smaller amount of material that achieves critical mass. So it's not simply the amount of stuff that is required, it's also other factors like some kind of neutron reflector can affect that. Okay. And there's actually a number of different things that the critical mass can depend on. So the critical mass, like we talked about before, is going to depend on the amount of stuff you have, but it also is going to depend on the type of fuel. So, for example, uranium 235 is not the only fissionable material. The different types of fissionable material are going to have different types of critical mass. So, uranium 233 is also fissionable, also plutonium 239, very, very commonly used. So, plutonium 239 is probably the most commonly used in nuclear bombs. Okay. And so, you have different types of fissionable material possible. Next is going to be the purity. Okay. And this is extremely important. We're going to talk more about this in our next slide here. But purity, or typically what's known as enrichment, is going to be extremely important. Okay. And so the more pure the material is, the smaller the critical mass needed. So if you have something that's not pure uranium 235, and typically you don't, let's say it's only 50% uranium 235 and maybe 50% uranium 238, you're going to need a lot more of that material in order to achieve critical mass. Also, the shape is important because again, this has got to do with those neutrons either initiating another nuclear fission process or those neutrons being escaping and going off and doing nothing. Okay, so the more round it is, the more you can decrease that surface area to volume ratio, the smaller your critical mass. So the less material you need in order to achieve that self-sustained chain reaction. Like I mentioned before, you can use neutron reflectors, and it's even affected by temperature a little bit. Now, you really don't need to worry about temperature too much, but the higher the temperature, the larger the critical mass needed. And that just means that you don't, if you're making a nuclear bomb, you don't want to have just barely the critical mass because as you initiate an explosion, right, your temperature is going to go way up, which could all of a sudden increase your critical mass somewhat, which might turn you from supercritical to subcritical. So you need to be careful about that a little bit. All right. Now, very important to this whole critical mass idea is the understanding of enrichment. Now, uranium, which is a naturally occurring element, right, is mostly uranium 238. Okay, so natural uranium, if we look at natural uranium right here, it's over 99% uranium 238 and only 0.7% uranium 235. Uranium 235 is the one that undergoes fission in a self sustaining chain reaction type process. Uranium 238 will not do that. So uranium 235 is less than 1%. Now, if you want to actually have this turn into, let's say, a nuclear weapon, you need to enrich that into over 90% uranium 235, which is often the most difficult part of making a nuclear weapon. It's not the making, the design of the nuclear weapon itself, it's the enriching of the uranium that is typically the most difficult part. Now, for a nuclear reactor, now there's different types of nuclear reactors, but oftentimes for the most common type of nuclear reactor, you're going to use low enriched uranium, which is going to be more or less 3 to 4% uranium 235. You don't want your nuclear reactor exploding, so you're not going to use highly enriched uranium. Instead, you want something that's around 3 to 4% of uranium 235, and that's going to enable you to get a higher temperature and to make power out of it, but you're not going to be able to have any kind of explosion out of 3 to 4% uranium 235. Okay, so how about these nuclear bombs? The very first types of nuclear bombs that were created by the United States in World War II and dropped on Japan were these two different types. The simplest type is going to be known as this gun type assembly. And it used uranium 235, so highly enriched uranium 235. And we had essentially two hemispheres of uranium 235, right? And so basically, you can think of two halves of a circle of uranium 235. And essentially, each of those two halves are subcritical. So they're not going to explode. They're not going to do anything. They're just sitting there. But if we slam these two things into each other so that you create a a whole sphere, so eventually these are going to come together to make a whole sphere. That sphere is now going to be supercritical and it's able to undergo a self-sustaining chain reaction and explode. And in order to make that come together, you typically have an ordinary explosives such as TNT or something else similar to that over here to shove those two hemispheres of uranium together. That's the most simple method. And that was used in the the little boy bomb that was dropped on Japan. Okay. The more sophisticated and now more common type of nuclear bomb that's used is known as the implosion type nuclear bomb. This is more efficient and it uses plutonium, which is actually easier to produce than highly enriched uranium. So it uses typically plutonium 239, and the plutonium is right here in the middle. So I don't know if you guys can kind of visualize this or not, but imagine some sort of hollow sphere of plutonium. Now, this hollow sphere, because of its shape, because it's hollow in the middle, and you basically just have this thin amount of plutonium all around, it's not going to be a critical mass. So it's going to be a subcritical mass, all here of plutonium. So this hollow sphere. But once you want it to explode, you have all these explosions all around it, which is going to create a very large pressure and cause this hollow sphere of plutonium to collapse on itself. And when it collapses on itself, it forms a ball of plutonium, which now, because its shape has changed, now is achieved supercritical mass, and it will undergo a self-sustained chain reaction and explode. Okay. Now, this hollow sphere of plutonium can be filled with nothing in the middle, or typically they will use some sort of neutron producing material right here in the middle, which will help initiate the nuclear explosion. There's a number of different materials that give off neutrons and undergo neutron decay, and you can put them right here in the middle to initiate that nuclear explosion. Or you can also boost it with things in the middle, like tritium, to increase the amount of the yield that you get from your nuclear explosion. All right. The very first nuclear bombs were both about 20 kilotons, okay, which is fairly small for a nuclear explosion, but extremely large for any kind of conventional explosion. So, what does it mean? 20 kilotons, kilo means 1,000. So, this means it was equal to 20,000 tons of TNT. Now, we'll put that into our ordinary terms. A ton is 2,000 pounds, or approximately 1,000 kilograms. So an ordinary bomb is very frequently about 1 ton. It's a standard bomb, might be about 1 ton of TNT. So one of these nuclear bombs was equal to 20,000 ordinary TNT bombs, all exploding at the same time. And in addition to that, you also have this nuclear fallout, the nuclear fallout, which can um, hurt people over a time after the explosion that are further away from the explosion. Okay, so we were talking about 20,000 ordinary TNT bombs. That was the strength of each of these. Incredible, incredible amount of power. Okay, where is all that power coming from? Now, during a nuclear fission reaction, what happens? A small amount of mass is lost. Yes, mass is lost. And that mass is converted into a comparatively large amount of energy. And it's converted into energy. Essentially, we can calculate the amount of energy that is converted to using this equation that Einstein came up with. That mass and energy are not completely fixed things, but you can actually convert mass into energy or energy into mass according to this equation. So E standing for energy, M standing for mass, and C is the speed of light. Now, light travels at a very, very fast speed. So we can imagine the speed of light, which is already a large number, 3 times 10 to the 8th meters per second. The speed of light is a large number, and then that large number squared. Now, this is a linear relationship, but we have an extremely large constant here on the right side. So a very small amount of mass that's lost is going to turn into a very, very large amount of energy. Now, this energy is related to the binding energy, and so essentially we can talk about binding energy. Binding energy is the energy that holds the nucleus together, and the higher the binding energy is, the lighter the atom is relative to the particles it's made out of. So you might think of protons, neutrons, and electrons having a particular mass, and they do, but the mass of protons and neutrons can change depending on what they're where they are, right? So a proton that's all by itself is going to have a different mass than a proton that's inside, and let's say, for example, an iron nucleus. So an iron nucleus, for example, iron 56 has got a number of protons and neutrons in it, and those protons and neutrons have a very large binding energy, and that binding energy is kind of what holds the nucleus together. And if that were to split, that binding energy were to decrease, and you were, in that case, to increase the mass. So what happens, let's say for uranium 235, okay, uranium 235, when that splits, you have an increase in binding energy, and that increase in binding energy corresponds to a release in a very large amount of energy. Okay, so going from uranium 235 to various different elements over here, what it turns into, whether it's krypton or whatever else elements that it turns into, that uranium 235, when it splits and increases its binding energy, is going to decrease in mass. Everything up here is a lighter mass in terms of the protons and neutrons it's made out of. When it increases its mass, when it decreases its mass, it's going to give off energy. If it were to increase its mass, it would need to absorb energy. But as it goes to a smaller particles, lighter particles, such as iron and other things, it's going to reduce its overall mass per nuclear particle and give off a whole lot of energy. Okay, so what about nuclear fusion? Nuclear fusion is kind of the opposite of nuclear fission. Nuclear fusion is a process where two nuclei fuse together to form a single element. Nuclear fission is splitting, and nuclear fusion is joining together of elements. Nuclear fusion is actually able to release much more energy than nuclear fission. Now, we already know that nuclear fission releases a very, very large amount of energy, but nuclear fusion releases even more energy than that. And nuclear fusion is actually the reaction that powers our sun, and all stars or more or less all stars throughout the universe. And one of the main reactions that occurs in our sun and other stars is this reaction right here. So you have here hydrogen combining with hydrogen to make helium. This is heavy hydrogen and heavy hydrogen. And when they combine to make helium, they release a very, very large amount of energy. Now, um, this is only one of the processes that occurs in the sun, but there's other processes too. So you, for example, you can take light hydrogen together and fuse that together to make heavy hydrogen, which you have here. And so hydrogen plus hydrogen can fuse together to make helium, and that occurs all the time in the sun, releasing a very, very large amount of energy. Okay. Now, in relation to these energies, it turns out that iron 56 is the most stable nucleus. Nuclei that are smaller or larger than that are going to be less stable. So, if you combine small nuclei to make medium nuclei, that's going to release energy. Or if you split large nuclei to make medium nuclei, that's going to also release a large amount of energy. Okay? So it's this medium size element, such as iron 56, that's the most stable or the lightest or has the largest amount of binding energy that everything wants to turn into. Okay? In both fission and fusion, mass is being converted into energy. All right. And so in both cases, you're losing mass, not just in fission, not just in fusion, but in both fission and fusion, you're actually losing mass and converting that mass into energy. Okay. And so we can see that right here in this diagram once again that we saw earlier. All right. Here we have over here, starting with uranium, right? You are splitting it and turning it into, let's say, a medium sized nucleus. And there you're losing mass, you are increasing binding energy, and you're giving off energy. Okay. If you start with hydrogen, where's hydrogen? Hydrogen's way down here. Okay. If you start with hydrogen and you combine hydrogen to make, let's say, helium, you're going to also increase the binding energy, lose mass, and release a whole lot of energy. Now, look at this. For going from uranium to, let's say, iron, you've got that amount of binding energy increase. But if you go from hydrogen way up to helium, that's a much, much larger amount of binding energy. So you have a much, much larger amount of energy that can be released when you undergo fusion of hydrogen to helium. Okay. The power of the first fusion bomb was more than 10 megatons. 10 megatons. Mega meaning a million or 10 to the sixth power. And that was equal to 10 million tons of TNT. Okay, this is just the very first fusion bomb. And that was equal to about 500 nuclear fission bombs dropped on Japan. So the power of a fusion bomb is enormous, much, much, much more powerful than nuclear fission bombs that have been used previously during World War II. Right? Now, we have since, or various different countries have since made even more powerful fusion bombs. And the most powerful ever that was detonated, now, supposedly, perhaps more powerful ones have been made, but the most powerful one detonated ever was the Tsar Bomba that Russia made and tested all the way back in 1961. And that was measured to be 57 megatons, 57 million tons of TNT in terms of its power. So here is a picture of the Tsar Bomba, and so it's big, but it's you can fit it in a building. It's not so big that you couldn't fit it in a building. So it's this big, and this is a picture of the fireball that it created, and it was dropped or it was exploded somewhere over the North Pole. Very, very powerful, and a test over the North Pole. Okay, so how do these nuclear fusion bombs work? All right, it's actually very difficult to achieve nuclear fusion. Nuclear fission is pretty easy to achieve. All you need for nuclear fission really is your critical mass. Once you have critical mass, boom, it blows up, nothing else, right? Nuclear fusion is much, much more difficult. And why is that? Right? Essentially, the main reason it's so difficult is because what needs to happen in nuclear fusion is that you need to take nuclei which are positively charged, right? All nuclei are positively charged no matter what the nucleus is composed of protons, which are positively charged, and neutrons, which are neutral. Okay. And they need to be squashed together somehow. Okay. But they're going to repel each other. And because they repel each other, there's an extreme amount of nuclear repulsion, and that energy needs to be overcome. So the way you overcome it is you need to have very, very, very high temperatures, and so that high temperatures can overcome that repulsion of the nuclei. And you need to have very high pressures, essentially, to squeeze these nuclei to get so close together that they'll actually fuse. Once you can get them to overcome that repulsion and get close enough together, they will fuse and release an enormous amount of energy. So, one of the most common designs for a nuclear fusion bomb is this. In order to achieve those high temperatures, they're actually going to incorporate a fission bomb inside the fusion bomb itself. So those fission bomb, the nuclear fission is going to enable you to get to the high temperatures in order for that nuclear fusion to take place. So in this case, you have a plutonium nuclear fission bomb, which once it explodes, this whole thing gets to be very, very hot. Plus, you have a whole bunch of neutrons that are all over the place. Plus, in here, you have some more fissionable material, whether it's plutonium or uranium, and also a tamper in here. So this tamper basically keeps everything there packed together, right? And the red stuff in here is your fusion fuel. This is the main fuel for your reaction of what you want to burn. Well, what is that nuclear fusion fuel? That nuclear fusion fuel typically is going to be lithium deuteride. So lithium hydride, as we know, lithium hydride is a simple compound of positively charged lithium and negatively charged hydrogen. And because it's an ionic compound, it's going to be a solid, right? And that's what you want, right? So you might think, okay, for a hydrogen bomb, you're going to use just simply hydrogen. But you can't just use simply hydrogen because hydrogen is a gas. Well, actually, you can, but you have to cool it down, and it's very impractical for making a droppable nuclear bomb with. So rather than just using pure hydrogen, you're going to make lithium hydride, but not simply lithium hydride, lithium deuteride. And that deuterium is basically heavy hydrogen. It's hydrogen that has a neutron with it. So one proton, one neutron, and that's going to be your deuterium. So lithium deuteride is a solid that we can pack into here, which is exactly what you want. You want something that's packable and storable when you make a nuclear bomb. So it's a solid that you can use, plus it's got a whole bunch of hydrogen really packed together, closely together. Okay? Because solids are fairly dense compared to, let's say, gases. Now, what happens is that when you have this nuclear fission bomb first explode, it's going to initiate a further nuclear fission of here, which is also going to explode, whether this is plutonium or uranium in here. That's going to explode, and it's going to cause it to force everything to go outward. Well, you also have a tamper here, which is going to stop it from going outward, and you're going to have an extremely high pressure that's going to occur right in here because of this design. And that high temperature from the nuclear explosion, plus the high temperature of this squeezing outward and squeezing all of this lithium deuteride together, is going to press those nuclei together. They're going to come together, and they're going to have nuclear fusion. Okay, so first you have here, this is your design. Then first you have your nuclear fission take place. That's going to cause a further nuclear fission on the inside, and it's going to cause compression here. And this nuclear fusion fuel, such as lithium hydride or lithium deuteride, is going to burn and explode and release so much more energy when the hydrogen combines to make helium. So that's it for today. Hopefully, you guys have learned something about nuclear fission and fusion. See you guys.